All right, thank you, Wes. Thank you, folks, for showing up today. Who wants to learn about IPMX? Anybody? Hey, everybody. All right, you came to the right place. Good, good. Okay, so I'm Jed Deame, as he mentioned. I'm one of the members of the activity group that's defining IPMX. And we've been busily going through creating all these new specifications. And they're all on the website, but I thought I'd give you a nice little overview today, kind of a simple, here's what they are, here's why they're important. Feel free to interrupt me at any time if you have any questions. So here's all the different specs that we have. We've been quite busy. We're up to -14. So I'll go through each one of these in some detail and show you. And these will all be on the website, ipshowcase.org, afterwards, along with this recording. Okay, well, what the heck is IPMX, right? Let's just start at the beginnings. So it's an extension of 2110. As you know, 2110 is the video over IP standard that the broadcast community has embraced 100%. Well, what about the Pro AV community? What about them? Can they leverage this? Well, yes, they can, but their requirements are slightly different. They need things like asynchronous senders. PCs typically aren't gen-locked, right? Well, how do we deal with that? I don't want to have to frame sync all my PCs. I want to maybe handle compressed. I want to run at 1 gig instead of 10 gig or 25 gig. I want HDCP. I want USB, KVM things. So that's really what we did in IPMX is we started with this foundation, proven foundation of 2110, and we add some components right on top of it that give you all these extra capabilities. It's also an open standard published by VSF, so it's not tied to any one particular vendor. And it allows you to build these low latency interoperable solutions, which is what end customers are asking for. Okay, here are the components, and here's where you can find them on the VSF website if you want to read them in detail. It's a little bit dry reading, so I'll give you a nice little overview today so you can see. And most of these are finalized. There's always some work going on, but the key specs that are needed to deploy systems today are final, and they're ready to go. And we've already done some interops. Okay, so we'll start with the first one is -0. That's an organization document. It's just informative. It just kind of gives you an idea of here's what all the specs are, and just like a one-liner title and a little paragraph description of what they do. The most important one I would say is TR10-1. That's the system timing. So we'll spend a little bit of effort on this. So first of all, it handles asynchronous sources, as we mentioned, things like PCs or Blu-ray players or whatever else you might have. It also describes what to do if PTP is present, how to handle that. A slightly different traffic shaping model. Traffic shaping means how do I send packets so I don't clog the switch? Those have been relaxed for Pro AV markets, and talks about the SDP. SDP is the session description protocol file, which is what senders use to tell receivers what they're transmitting. So we'll talk through all that. So that's the high level. Let's dig into the details of these. So how do we handle this asynchronous media, and how do we handle this timing? So there's two things that we do in IPMX. One is we send an RTP sender report. The sender tells the receiver what its current resolution is or audio rate constantly, once a frame. In 2110, the resolution doesn't ever change, so we didn't really need that, but in IPMX we do. And then we also have this way to recover the clock timing in the receiver. So that's what the second one is, sender timing recovered with clock recovery. So you can have about a 2-line latency from an asynchronous sender all the way from the sender to the receiver. Asynchronous sender, asynchronous receiver, 2-line latency all the way through. Whereas if you try to do it in 2110, it would be up to a frame latency. So very important. Well, what do we do with PTP? Well, if you have it, it'd be nice to use it. It'd be nice to lock everybody to it. So that's what we spec in IPMX. If you have a PTP clock in your sender, you shall lock to that clock. Otherwise, use your internal clock. Fine. You can also be a PTP leader. One other thing that was not convenient for Pro AV or non-on-air applications is they didn't want to buy a big $10,000 PTP generator for the entire network. So what a lot of vendors are doing is they're putting like little small PTP generators in each of their devices, and they just nominate one of them to be the PTP master. And so some of the restrictions have been eased to make that available in a low-cost solution. Traffic shaping, as I mentioned, this is the way to prevent clogging up your switch and clogging up your network. Those have been relaxed a little bit because typically in Pro AV you might not have 10,000 sources all on the same network. So doing things like what we call wide receiver that allows you to be very flexible on the timing so you can have a PC-based sender. One of the big things the Pro AV guys want is, I just want to have a PC and I want him to be able to use his CPU to generate a stream and send it, but in a compatible way, in a 2110 IPMX compatible way. So we had to relax the timing a little bit on that. And some things in the SDP file to say, hey, I'm an IPMX sender, so the control system knows what to do with that. Okay, the second piece that we talked about was the RTP sender reports. Again, this is how the transmitter tells the receiver what it's doing, what its resolution is. It's mandatory. It must be sent once per frame or field if it's interlaced for the video. For the audio, it's sent once every 10 milliseconds. For the ancillary, anytime a new timestamp is sampled. What are these reports? Well, it's just a packet, right? It's just a TCP/IP packet that's sent, a UDP packet that's sent to the receiver, but it's sent at a port number of +1 of the media, so you don't have to figure out what it is. The receiver knows if I'm receiving media on port 10, this sender report will be on port 11. Simple, easy. Right? We try to keep things simple for implementers and for customers. And it's got this media block extension. So the information in this sender report, it's got the orange stuff, which is some sender information, some timestamps. And then it's got this info block extension, the IPMX tag, some clocking information. But the most important thing is this green thing, this media information block that has the meat of the information. So what does this really look like in a real system? Well, again, I've got this asynchronous sender. It's a PC. He's trying to send video, audio, and ancillary streams, just like you would in 2110. But we're also going to send a video, audio, and ancillary RTCP packet, a sender report. And it's got this info, and again, the media information block to tell the receiver what's going on. So I'll go through each of these, the video, the audio, compressed one at a time, and we'll dive into what this info block is so we can see what we're sending. So for uncompressed active video, this is TR10-2. So each of the dash numbers in TR10 are a different type of essence, we call it. It's video, it's audio, it's ancillary, it's compressed video. So -2 is the uncompressed active video. So we referenced a lot of the 2110. We're not trying to reinvent the wheel here, but we're putting additional metadata in the SDP file, and we're able to support a lot of different sampling schemes that weren't supported before, things like RGB, things like 8-bit, in addition to the 10-bit SDI type sampling. And then we use a 90 kilohertz media and RTP clock. But here's, again, the meat of this sender report. This is everything the sender sends the receiver, the width, the height, the total number of pixels, frame rate, sampling, et cetera, all the way up to things like pixel clock. So everything the receiver needs to know to lock to it without having the control system need to get involved again, like 2110 needs. 2110 would have to tell the receiver this explicitly every time something changed. But in IPMX, you could just turn off the control, you could route something, turn off the control system, and you could change your resolution on your sender, and the receiver would follow that and figure it out. Okay, well, what about audio? Well, -3 is the pulse code modulated digital audio, very similar to 2110-30, which is based on AES 67. We use a sample rate of 48 kilohertz at either 16 or 24 bits. 44 kilohertz, 96 kilohertz are recommended, but not required. 48 kilohertz is required. Sample clock and RTP clock are the audio sample rate, and we meet the level A conformance level, if you know what that is. You can read the specs to find the details of that. But again, the point of this slide is to show you what information is sent from the sender to the receiver, sample rates, sample size, channel count, packet time, channel order, and sample rates. Okay, next component, as you know, in 2110, you've got video audio. The third thing is ancillary data. We also need to support that. So we're referencing 2110-40. We're locking the media clock and RTP clock to 90 kilohertz. And there's fortunately no media info block required because all the information for ancillary is embedded in the packets themselves. One other thing we talked about, HDCP. You don't get that in 2110. Well, the Pro AV guys want it. Unfortunately, Laptops like to put out HDCP, Blu-ray players like to put out HDCP, other media players. How do we handle it? Well, we're not reinventing the wheel here. We're not trying to re-encode or re-encrypt anything. We're just using the existing encryption that's there. And we're following the recommendation of DCP LLC, which is a regulatory organization that manages HDCP. So it's 100% legal. We didn't just make something up here. And it's a key exchange mechanism. So we use the same keys that HDCP uses. So if a PC is talking to a monitor and sending HDCP, we just intercept those and hand them over IP from A to B. I've got a picture coming up that shows it in some more detail, but that's really all it is a mechanism to move keys back and forth. This should make it a little easier to follow. If you're familiar with how HDMI does it, you've got these TMDS lines. This is your red, green, blue pixel data, and then there's a separate pair of wires. This is the HDMI cable that we're looking at. In the cable, there's a pair of wires. It's I²C, and that's where the keys go back and forth. And they call that HDCP HDMI. Well, how would you do that over IP? So this is now your IP channel. You're sending this over twisted pair, usually RJ45s. You're sending your RTP packets now. Instead of just raw pixels, you're sending packets for red, green, blue, audio, video, ancillary. But now we have a separate TCP IP channel for this communication of the keys back and forth. So it's kind of tricking HDCP. So the sender and the receiver don't know that we're doing this. We're just transporting the keys over that same IP network. Okay, next, FEC, forward error correction. What is that? Why do we need it? As you know, 2110 is typically a redundant system. You've got full redundancy, 2 fibers for each interface. That's maybe a little much for non-on-air applications or Pro AV applications. Or cost-sensitive applications where they don't want to buy 2 switches and twice the network infrastructure. So an alternative is we use this thing called FEC that allows us to use some clever math and send a couple extra packets and allow for packets to be lost and then recovered. How does that work? Well, these extra packets are calculated with a fancy algorithm. It's not really that fancy. You kind of lay your packets into 2 columns here, and then as you're transmitting, you're accumulating. You're doing this function called exclusive OR, which every byte of every packet you're comparing to the next one and saying if you're either true or you're not. So if one is a 1 or the other is a 1, but both of them aren't 1s, then you set this as a 1. So you're making a new packet with a mathematical representation of 16 previous packets. So if you lose, for instance, number 4, you can recalculate it based on this packet. So very handy way to add some resilience to your network without having to send redundant interfaces. The specs are defined in TR10-6. It's building again on the SMPTE 2022-5, trying not to reinvent the wheel again. It's optional for senders, but receivers must be able to tolerate these extra packets, so we just throw them away if they didn't know what to do with them. And similarly to the sender reports, we wanted to make it easy for the receiver to find these things, so we use the same media port +2. So the media port is sending your essence, +1 is your sender report, +2 is your FEC. So it is all communicated, but it makes it easy to calculate. The video, as we showed, does 16 rows and 2 columns. The audio just duplicates packets because the data rate's pretty low. Okay, one of the other things we talked about that's nice for IPMX is compressed video, right? You'd like to be able to send 4K P60 over a 1 gig twisted pair fiber. Great. How do you do that? Well, you follow a spec like this one, TR10-7 for compressed video. This one will even let you go variable bit rates for things like H.264 HEVC to get it way down, even under 100 megabits. It references SMPTE 2110-22, which is the compressed video transport spec. There's some details on the clock, and there's some parameters that are added to your SDP file. But again, the most important thing is this RTP sender report. Normal information that you would send if it was uncompressed video, plus some additional information for compressed video like encoding range, codec information that specifies bit rates and profiles and levels. so the receiver can interpret what's coming in a plug and play type manner. Next, NMOS. As you know, NMOS is the control system that we use in 2110 so that senders and receivers can be connected seamlessly by just pressing a button or clicking a button, one click, so no typing required. Just like an SDI panel, you connect a sender to a receiver. Well, we want to do the same thing in IPMX. So we built upon the current NMOS, so it's the same NMOS controllers, but we've added some features to it to make it easy for the user. So that's what TR10-8 specifies. We've added, so we're also specifying that we need to do the service discovery of unicast and multicast, specifying unicast as a preference. We require natural grouping, which means the audio, the video, ancillary should be grouped together and named together so they show up logically in the control panel. We show we use the latest ISO 5. We publish some constraints. So what that means is capabilities of the senders and receivers are published to the control system so it can tell, it doesn't try to route an uncompressed signal to a compressed receiver, for instance, or vice versa. So it gives the user hints so it can't connect things that aren't compatible. If you're JPEG's XS, you must follow 06. Yes, sir, question. Yes, there are. There are a few. The Matrox controllers, one conduct IP that we use in our demo that supports a lot of these capabilities. So yep, they're catching on very fast. So good question. Okay, the next thing, what other things would you might want to do in a Pro AV application? You might want to do a video wall. You might want to do receiver synchronization. How do you do that? Well, we have this thing called external link offset delay, and that is a way that the receiver can tell the sender, it can tell the control system about the delays of different senders that may be asynchronous. So instead of reading all that text, I'll show you the example here. You might have 3 different senders that are all slightly offset in time from each other. They're different asynchronous sources. That's what you're going to expect. So what the receiver does is he measures the minimum and maximum of each of these, tells the control system, and then he finds a nice least common denominator to line them all up. So that allows us to do video walls in IPMX without requiring any special electronics. We can make sure that we take into account any delays in the receiver, any delays in the network, and synchronize all those. Okay, what else do we have? We have -9. That's what we call the system environment and device behavior. If you're familiar with 2110 TR 1001, that's kind of a guideline that says here's how to build systems around 2110. This will be the equivalent document. This is still in development, but it'll be system level guidelines of how to build systems, how to select switches, those sorts of things. Okay, moving on, -11. This is the compressed video specification. This is the one that's most commonly used today because JPEG XS is the codec that's predominantly used in IPMX. It's not the only one, right? We're supporting multiple codecs. But if you're going to support JPEG XS or some constant bitrate compressed video signal, this is the spec that would govern that. Some modifications to the SDP file, as are mentioned there, but again, the key information is this RTP sender report that provides all the information that a receiver will need to see the sampling rates, levels, sublevels, all those sorts of things. Okay, what about AES3 audio? We might want to transport that from A to B. How do we do that? Well, -12 specifies how to do AES3, which is commonly used for compressed audio. So stream media clocks run at 44 kilohertz or 48 or 96. 48 is required, the others are optional. Here's the sender report, which has more audio-related things. As you can see, sample rates, channel counts, packet times, and codec information. Okay, -13. So now we're getting into some things that really weren't possible in 2110 at all, that we've had a lot of requests for. How do we handle privacy and encryption? And you could say, well, we could use HDCP. HDCP is a way to encrypt data, but maybe there's maybe it's not the best way. Maybe it's not secure enough. Maybe it's a medical application or government application or even a high-level content. You could actually use your own encryption scheme. So we created this mechanism where other encryption might not be appropriate, or it might be too onerous to get keys from the HDCP guys. You just put in your own codec, your own encryption, and you follow this PEP, this privacy encryption protocol, and you can encrypt your content from A to B. USB, big request that we're getting from the Pro AV guys. What if I want to do like a KVM extension? I want to extend my PC to someplace else. I'd like to use IPMX for the video. That's great. That means I can send the video from my PC to many different places. Well, what if I want to control that PC with a remote keyboard or mouse? Okay, well, let's use USB. So that's what TR10-14 specifies. It's based on USB 2.0. Handles most common use cases. Here's a quick example of how this would work. You've got your receiver that's IP connected to your sender. You can see you've got your keyboard and your mouse on the other side of the IP network connected to some device here. And then you've got these blocks in between that are just translators. You're translating the USB protocol to this communication mechanism, this USB over IP. So we're packetizing the USB data and moving it across the network so that any of these remote devices can then connect to that receiver. Detailed spec, you can read it if you want, but this is the high-level overview of what you get. Okay, well, in summary, as we mentioned in the beginning, IPMX builds upon this proven foundation of 2110. It adds in capabilities that are needed for asynchronous sources that handle other use cases in other markets, things like Pro AV, medical, some military applications, etc. It's an open spec. There are lots of other solutions out there to do compressed video over IP, but this is an industry standard way, published in an open spec, not reliant on a single vendor. They're published on the VSF website and ready to design against today. We've been through interops. They're ready to go. There are quite a few IPMX products on the market today. If you'd like to see some of them, you can run around the show. We have got an interop demo at our booth in the South Hall, Nextera Video. You can look us up. We'll be happy to show you this in more detail. Thank you very much.